Welcome students once again into the class of number theory. And in the previous video, I left you with this question on the board and I gave this question to you as an exercise to solve, and I promise you that in the next video, in the coming video, I'll solve this question. So if you have solved this question, that's very well, and if not, then I'm going to solve it. The first part of this question I have solved in the previous video, that if m is greater than n, then a raised to the power 2 power n plus 1 is a divisor of a raised to the power 2 power m minus 1. This part we have solved in the previous video, and now I'm moving on to the next part, that if m is not equal to n, then GCD of a raised to the power 2 power m plus 1 and a raised to the power 2 power n plus 1 is 1 if a is even, and it is 2 if a is odd. This part we are going to prove in this video now, and then we will move on to the more and more questions of congruences. So this GCD, we have to show that it is either 1 or 2 depending on whether a is even or odd. So suppose this GCD is D. Let a raised to the power 2 raised to the power m plus 1 and a raised to the power 2 raised to the power n plus 1, let the GCD be D. We know that if a and b are having GCD D, then D is a common divisor of both these. That means D divides a and D divides b. So here again, the same thing I'm going to use, that this means D divides a raised to the power 2 raised to the power m plus 1 and D divides a raised to the power 2 raised to the power n plus 1. Now take any one of these two, either this or this. So let me take this one, the second one. D divides 2 raised to the power, a raised to the power 2 raised to the power n plus 1 means, if I convert this divisibility equation into the congruence equation, what I am going to get is a raised to the power 2 raised to the power n is congruent to minus 1 modulo D. This. And we know that if a is congruent to b modulo m, then any power of a is also congruent to same power of b. That means a raised to the power k is congruent to b raised to the power k modulo m for every integer k. So what I am going to do here, raising both sides to the power 2 raised to the power m minus n. 2 raised to the power m minus n, both sides. So what this will give? This will give on the left hand side power to power. That means x power a power b. We know that it is x raised to the power a into b. Power will be get multiplied. 2 power n multiplied by 2 raised to the power m minus n. Since base 2 is same, powers will be added. N plus m minus n, n will be cancelled, and you will be left with a raised to the power 2 raised to the power m. So a raised to the power 2 raised to the power m on the left hand side is congruent to, on the other side, 1 raised to the power anything. It is minus 1, minus 1, and minus 1 raised to the power even, because 2 raised to the power something. M and n are not same. M and n are not same means this number is not 0. So if it is not 0, then 2 raised to the power any non-zero integer is even. Minus 1 raised to the power even is 1. So this is going to be equal to 1 modulo D. Once again, convert it into the divisibility now. So what you will get is that D divides a raised to the power 2 raised to the power m minus 1 now. Earlier you have D divides a raised to the power 2 power m plus 1, and now you are having D divides a raised to the power 2 power m minus 1. If a divides x and a divides y, then we know that a divides x plus y as well as a divides x minus y. So here I am going to use the fact minus. D divides this number, look into this, D divides this and D divides this, means D divides their difference. And what is their difference? D divides this minus this. When you will subtract this quantity from this, a raised to the power 2 power m will be cancelled out and you will get 1 plus 1, that means 2. So d divides 2 and d divides 2 means d is 1 or d is 2. Either d is 1 or d is 2. Now it depends upon a. If a is even, this is even plus 1 is odd, this is even plus 1, it is odd, odd and odd. Both quantities are odd. And if both quantities are odd, 2 cannot be a divisor of this both of these. And if 2 cannot be a divisor, 2 cannot be the common divisor. So d cannot be 2 in this case, that case. So what will happen? D will be equal to 1. So if a is even, both these quantities are odd, so GCD will become 1. And if a is odd, then odd. A is odd raised to the power anything is odd plus 1 is even, this is even, this is even. Both of these are even. That means 2 is a common divisor. But greatest common divisor is either 1 or 2. And 2 is also a divisor, common divisor. So definitely the greatest common divisor will be 2 in that case. So the question is solved in this way. So I think either you must have solved this question earlier before my starting this video, and if not, then I think now you have understood how to solve such questions. So I'm moving on to another question now. So next question what I'm going to take is write down question using congruences show that 43 divides 6 raised to the power n plus 2 plus 7 raised to the power 2n plus 1. We can show this by using principles of mathematical induction also, but here the question is use congruences to prove this. So how to use congruences to prove divisibility of this type? Very easy, it's not difficult at all. Look at the solution, how to solve it, how to prove it. This is your 6 raised to the power n plus 2 plus 7 raised to the power 2n plus 1. I can write it as 6 raised to the power n into 6 square plus 7 square raised to the power n into 7 raised to the power 1. Just broken the powers. And now it is 6 power n into 36, 6 square is 36, plus 7 square is 49, so it is 49 raised to the power n into 7. So these two quantities are same. This is your x, this is your y, x is equal to y. And we know that if x is equal to y, then x is congruent to y modulo n for every n. For every n. So here again this x and this y, they are same. Because just by solving this we have obtained this. So they are equal. And if they are equal, then they can be put in congruence relation to each other modulo any natural number, and that natural number I am going to take as 43 because I require this one. So what I am going to do, this 6 raised to the power n plus 2 plus 7 raised to the power 2n plus 1 is congruent to this quantity 6n into 36 plus 49 power n into 7 and modulo 43 because I need modulo 43. And we know that in congruence relations, if A is congruent to B modulo n, and if we divide A or B or any quantity in this congruence relation by n and we get the remainder R, then that particular quantity can be replaced by R. Suppose here you divide A by n and the remainder is R, then you can replace this A by R. It is a property of the congruence relations. Here the same thing I am going to do. It is 49, and if you divide 49 by 43, what will be the remainder? Definitely the remainder will be 6. So you can replace this 49 by 6. And now 6 power n is here, 6 power n is here, you can take out 6 power n as common. So 6 power n common, you will get 36 plus 7 modulo 43. This is congruent now. And what is 36 plus 7? 36 plus 7 is once again, it is 43. So into 43, modulo 43. I am writing plus 0 here. I am writing plus 0 here because a plus 0 is always a. Once again, here you are getting 43 and this is a congruence relation. In a congruence relation, once again, repeat the same property. Divide this 43 by 43 and what will be the remainder? Obviously it will be 0 because 43 is completely divisible by 43. So this 43 can be replaced by 0. And 6 power n into 0 is 0. 0 plus 0 is 0. So you are going to get a 0 here. So the right hand side is 0. And what is your left hand side? Is same. 6 raised to the power n plus 2 plus 7 raised to the power 2n plus 1. This is a congruence relation. A is congruent to B modulo n. And if A is congruent to B modulo n or modulo m, then what it means in divisibility? That m divides A minus B. So this means your m means 43, divides A minus B. This is your A, 6 raised to the power n plus 2 plus 7 raised to the power 2n plus 1 minus 0. Minus 0 is meaningless, so I am not writing here minus 0. So this 43 divides this quantity and this is what we wanted to prove. So in this way, using congruences, we can prove the identities related to the divisibility. And we can also find remainders when a large quantity is being divided by some prime number or some other any number. We can find the remainders. And so one such question I am going to solve here now. Write down the question. Find out the remainder. Find out the remainder when I am taking a bigger quantity, when 2, 3, 4, 5 raised to the power 6, 7, 8, 9 is divided by say 13. So if we divide this quantity 2, 3, 4, 5 by 6 raised to the power 6, 7, 8, 9 by 13, what will be the remainder? The remainder we have to find, and we will use once again congruences to simplify this question very easily in just 2 or 3 or 4 steps. So first of all, to find the solution, what you have to do, divide this 2, 3, 4, 5, 2, 3, 4, 5, that means base of the number, by this 13. Dividing, you will get 1 here, 13, then 1, 0, 4, then once again this is 8 I think, 1, 0, 4, and this will be cancelled, 0, 5 will be taken here, no more division, so 0 and 0, 0, so 5 will be the remainder. When you divide this quantity by 13, you are getting 5 as remainder. So what the congruences says in such a case, that this quantity is congruent to 5 modulo 13. So I am writing here this 2, 3, 4, 5 is congruent to 5 modulo 13, that we have obtained by using the simple division process, by obtaining the quotient and remainder. In fact, there is no need to find quotient, but it will automatically come when we will go on division. So we just needed remainder. So this is congruent to 5 modulo 13, but the process is not completed because we are having 2, 3, 4, 5 raised to the power 6, 7, 8, 9. Once again, if A is congruent to B modulo M, then A raised to the power n is congruent to B raised to the power n modulo M for every n. So take power 6, 7, 8, 9 both sides. So what you are going to get is that 2, 3, 4, 5 raised to the power 6, 7, 8, 9 is congruent to 5 raised to the power 6, 7, 8, 9 modulo 13. And this power, these powers now I am going to break. Why? Because I want to reduce this quantity 5 either to 1 or to minus 1. If I get 1 or minus 1 here, then 1 raised to the power anything is 1, and minus 1 raised to the power even is 1, minus 1 raised to the power odd is minus 1. So my question will become easy. So what I am trying to obtain a 1 or a minus 1 here. And for that, what I have to do? We know that 5 square is 25, and 25 is congruent to minus 1 modulo 13, because 13 divides 25 minus 1, that means 26. So 5 square I will have to use to reduce this quantity. For that, I am writing this as 5 square raised to the power. Now divide these 6, 7, 8, 9 by 2. So what you are going to get? 3, 9, 4 and 1 will be remainder. So that 5 raised to the power 1 I am writing separately modulo 13. You can easily check 2 multiplied by this quantity plus 1 is 6, 7, 8, 9. So my division process is very much correct. Now this 5 square is nothing but it is 25, and we know that 25 is congruent to minus 1 mod 13. So this 25 can be replaced by minus 1. So I am replacing this 25 by minus 1 because the congruence is modulo 13, and anything can be replaced by its remainder when divided by 13. Okay, minus 1 raised to the power even number. This is an even number because the last digit is 4. Minus 1 raised to the power even number is 1. So this whole quantity is equal to 1. And what you are going to get on the right hand side, the left hand side is your 2, 3, 4, 5 raised to the power 6, 7, 8, 9 is congruent to right hand side is 5 modulo 13. And that means if you divide this quantity by 13, what the remainder you are going to obtain is 5. And that is your question. Find out the remainder when this quantity is divided by 13. So your answer is 5. So remainder when this quantity 2, 3, 4, 5 raised to the power 6, 7, 8, 9 is divided by 13 is 5. So this is one of the question. So I can take one more question of this type to just for practice purpose. Just for your practice, I am taking another question of the same type to create confidence in you that you can solve such questions very easily. So another question of the same type I am taking here once again. So solve this question now. Find out remainder. Find out remainder when 1 raised to the power 1 is divided by say 9 in this case. Earlier I have taken 13, now I am taking 9 just to make the question a little bit different. And solution is on the same lines. First of all, you divide this 1 by 9. So it is 1, 9, 2, 1, 2, 18, 3, 1, 3, 27, 4. So your 1 is congruent to 4 modulo 9 because I need the quantity, the remainder and the divisor. So 1 is congruent to 4 modulo 9. But the process is not over because I need 1 raised to the power 1. So raise both sides to the power 1. So it is 1. It is again 1. This is okay now. Now we are to simplify this quantity. 4 raised to the power 1. Now once again I want here either 1 or minus 1 because that will help me to solve out the problem quickly. 4 square is 16 and 16 divided by 9 will give you the remainder 7, which will not work. So move on to the next power, 4 cube. 4 cube is 64, and when you divide 64 by 9, what the remainder you are going to obtain is 1, and that will work. So I'll break this now as congruent to this 4 raised to the power 3 raised to the power, now divide 1 by 3. So divide by 3, you will get here 3, then 2 1, 2 1 will be 7, then 1 will be 0, and again 1 will be the remainder. So into 4 raised to the power 1 is here, modulo 9, and you can check 3 multiplied by 370 plus 1 is 1111. It's complete. Division is okay. Now this 4 cube is 64, and we all know that 64 is congruent to 1 modulo 13. 64 is congruent to, sorry, not 13, it is 9, sorry. It is 9. So 64 is congruent to 1 modulo 9, because 9 divides 64 minus 1, that is 63. So this 64 can be replaced by 1 now. So I am replacing this 64 by 1. 1 raised to the power anything is 1. So this quantity is going to be equal to, congruent to 1. And what you are left with is congruent to 4 modulo 9. So 1111 raised to the power 1111 is congruent to 4 modulo 9, means remainder when you divide 1111 raised to the power 1111 by 9 will be 4. So your answer is 4 this time. And more questions are there of that kind for your practice. At the end of this chapter I will give you an exercise. Many questions will be there for your practice, but now at this position we are solving more and more questions. Another question I am going to solve for you. Write down the question. Show that the question is once again very easy. Show that 11 divides 2 raised to the power 15 into 14 raised to the power 40 plus 1. Question is very easy. It is just for your practice. I am taking practice questions now. No new concept. It is based on the concepts we have already covered. So what is the solution? Look at the solution now. Concentrate on this quantity. 2 raised to the power 15 into 14 raised to the power 40, and what it is congruent to modulo 11. That is our basic problem. So this 2 power 15 is okay, no problem, it is okay. Now this 14, it is in the base, and anything in the base can be replaced by the remainder obtained, the quantity by the modulo quantity, that is 11. So divide 14 by 11, and what is the remainder is 3. So you can replace this 14 by 3. So it is 3 raised to the power 40. And now reduce the quantity. How can it be reduced? This 2 power 5, 15, you can write 2 raised to the power 5 raised to the power 3. 5 3s are 15, it's okay. And this 3 power 40, you write 3 power 5 raised to the power 8. Once again, it's okay. It is 2 power 5. 2 power 5 is 32. And you know very well that 32 is congruent to minus 1 modulo 11, because 11 divides 32 plus 1. So this 2 raised to the power 5, I can replace this by minus 1 now. I replace this by minus 1. And what is 3 raised to the power 5? 3 raised to the power 5 is 243. And 243, if you divide 243 by 11, it is 2, 22, 2, 3. And if you take 2 once again, 24, so minus 1 will be remainder again. I am taking negative remainder, no problem. I can take negative remainder in the case of congruence problems. So this 3 power 5 can also be replaced by minus 1. So it is minus 1 cube is minus 1, and minus 1 power 8 is 1. So it is minus 1 into minus 1 modulo 11. So it is minus 1. But what you have obtained, look at, you have obtained that 2 power 15 into 14 power 40 is congruent to minus 1 modulo 11. This you have obtained. This is a congruence equation. Convert into divisibility equation. What you are going to get is that 11 divides 2 raised to the power 15 into 14 raised to the power 40 plus 1, and that was your question. So we have arrived at the conclusion what we wanted to prove. So this is another question for your practice, that this type of questions may be there in your examinations, in your question paper. And let us have another question. Another question I'm going to solve now is, show that for any n belonging to the set of positive integer or set of natural numbers, you can say anything, either your n is congruent to 2 mod 3 or n square is congruent to n mod 6. For any natural number n, either this is true or this is true. And the proof is once again not difficult, because we are using congruences, and congruences is a technique, is a special type of tools which makes difficult questions very easy. So it is another question which is looking a little bit difficult, but is very easy because we are using the tools of congruences. So how to solve it? Solution now. Take any natural number n, let n belonging to n be arbitrary. Then there are three possibilities. If you divide this n by 3, either your remainder is 0 or 1 or 2, there is no fourth possibility. So your n is either congruent to 0 mod 3, or n is congruent to 1 mod 3, or your n is congruent to 2 mod 3. So there are three possibilities. Either remainder will be 0 when n will be divided by 3, or remainder will be 1 if n is divided by 3, and the last possibility is that the remainder will be 2 if n is divided by 3. If the third case is there, then we have nothing to prove because it is as one of the results. You are having this n congruent to 2 modulo 3 as one of the results. So if this case is true, we have done. So this case is already done. That means in these two cases we will have to prove this. And that's again very easy. I am taking the cases separately. This case and here I am taking this case. If your n is congruent to 0 mod 3, definitely n square is also congruent to 0 mod 3, taking power to both sides. Now n square is congruent to 0 mod 3 and 0 is congruent to n mod 3. A is congruent to B, B is congruent to C, so A is congruent to C. This means your n square minus n is congruent to, n square minus n is congruent to 0 mod 3. Or you can say that subtracting from this congruence equation, you have subtracted this congruence equation. N square minus n is congruent to 0 minus 0 modulo 3. So we have obtained this result. Now this n square minus n is also congruent to 0 mod 2. Why? Because n square minus n means n into n minus 1. And n minus 1 are consecutive integers. If there are two consecutive positive integers, then definitely one of them is one of them is even. Either this is even or this is even. If this is even or this is even, the product will be divisible by 2. And that's what I have written, that if this quantity is divided by 2, the remainder is 0 because this quantity is even. If n is even then this quantity is even. If n minus 1 is even, the quantity is once again even. And even quantity divided by 2 will give you remainder 0. Now n square minus n is congruent to 0 mod 2 and n square minus n is congruent to 0 mod 3. And we know that if A is congruent to B mod n and A is congruent to B mod m, then A is congruent to B modulo mn also. So here n square minus n is congruent to 0 mod 3 and n square minus n is congruent to 0 mod 2, means n square minus n is congruent to 0 modulo 2 into 3, that is 6, and we have proved. You can take n to the other side and you have proved the result. The other case is also similar. In the other case, your n is congruent to 1 mod 3. Squaring both sides, you will get n square is congruent to 1 mod 3. And once again, subtract this congruence from this one. So n square minus n is congruent to 1 minus 1, that is 0 mod 3. So you have obtained the same result. And this one is already there. I have already explained this. Here we have explanation of this. And once again, these two congruences will lead to this one, which is our required result. So for any integer n, either n is congruent to mod 2, n is congruent to 2 mod 3, or n square is congruent to n mod 6. So I'm going to stop this video here. In the next video we are having more and more questions on congruences. Till then, thank you once again.